Previously, we covered the core foundations. Now, in part 6, we tackle Mars, moons. Mars, episode 6, moons. Mars has 2 moons. For decades, we barely paid them any attention. But the closer we look, the more these 2 small, battered objects seem to hold genuine clues about how the inner solar system formed, and possibly about Mars itself. In the last episode, we covered Mars's atmosphere, thin, cold, and chemically active, in ways scientists are still working to understand. Today the question is simpler on the surface, but surprisingly deep once you dig into it. Where did Phobos and Deimos come from? That question has been sitting unanswered for well over a century, and right now, 2 active space missions are closing in on the answer. Let's start with the basics. Mars sits, on average, about 228 million kilometers from the Sun. A small, rocky world, about half the diameter of Earth, with gravity roughly 38% of what you'd feel standing on the surface here. Its carbon dioxide atmosphere is thin. Surface temperatures swing between around 20 degrees Celsius on a warm afternoon near the equator, and minus 125 at the poles in winter. Geologically, it's extraordinary. Climatically, it's hostile. Astrobiologically, it's one of the most important targets in the solar system. And orbiting this world are 2 of the strangest moons anywhere in the inner solar system. Phobos and Deimos, named after the sons of Ares in Greek mythology. Fear and dread, roughly translated. Discovered in August 1877 by American astronomer Asaph Hall, using the Naval Observatory's Large Refractor Telescope in Washington. Hall had almost given up the search the night before he found them. His wife, Angelina, apparently convinced him to keep going. Both moons of Mars were found within a 2-week window, almost by persistence alone. Here's the first thing that surprises most people when they see the numbers. Phobos is tiny. A mean diameter of roughly 22 kilometers, and it's not even a sphere. It's a lumpy, irregular object, shaped a bit like a potato. Deimos is smaller still, about 12 kilometers across. Neither has enough mass to pull itself into a round shape under its own gravity. These aren't moons in the way we think of our moon, or even Jupiter's large moons. They're small, battered, crater-covered rocks, orbiting a planet they seem almost too small to belong to. Which raises the question that's been nagging at planetary scientists ever since Hall pointed a telescope at them. Where did they actually come from? There are 3 serious hypotheses, and each one tells a different story about the early solar system. The first is capture. The idea is that Phobos and Deimos were once asteroids drifting through the inner solar system, and Mars's gravity snared them into orbit. Plausible on the face of it. Their irregular shapes are consistent with asteroid-like bodies, and early spectral observations suggested their surfaces might resemble certain carbon-rich asteroid types. But capture is dynamically difficult. For an object to settle into a stable orbit, it needs to shed energy at exactly the right moment, and doing that without a dense atmosphere or a third body to absorb momentum is genuinely hard to arrange. Not ruled out, but the circumstances required are difficult to model convincingly. The second hypothesis is in situ formation. The moons formed right there, in the Martian system, from a disk of material surrounding early Mars, similar to how Earth's moon is thought to have formed from the debris thrown out by a giant impact. Their stable, nearly circular orbits fit this story reasonably well. The problem is composition. If they condense from Martian material, you'd expect their surfaces to reflect that, and the remote sensing data has been ambiguous at best. They don't obviously look like Mars. The third hypothesis is a giant impact. A large object struck early Mars, throwing debris into orbit, and Phobos and Deimos coalesced from that material. The orbital characteristics work fairly well, and some modeling supports it. But once again, the compositional question hangs in the air. Here's what makes all of this so frustrating and so interesting. We don't actually know what Phobos and Deimos are made of. Not at the level of detail you'd need to confidently choose between these hypotheses. Remote sensing gives you surface reflectance, something about what's on top, but not what's underneath, or what the bulk composition really is. That's the open-loop 2 missions are now trying to close. JAXA's MMX mission, Martian Moons Exploration, launched in September 2024 and is due to arrive in the Martian system in 2025. It'll conduct close flybys of both moons, and crucially, it will land on Phobos and collect a surface sample of at least 10 grams, returning it to Earth in 2028. The first sample return from the Martian system ever attempted. If it works, the origin question could finally be settled. Material that looks like Mars points toward the impact hypothesis. Something resembling a primitive asteroid shifts the balance toward capture or early disk formation. ESA's HERA mission launched in October 2024 with a primary target of the Deimos system, the site of NASA's DART impact test. But its methods for characterizing small bodies are directly relevant to how we'll eventually study Phobos and Deimos in finer detail. Real momentum, then. The moons of Mars have gone from footnotes to active science targets, and the next few years are likely to change what we know substantially. Let's look more closely at Phobos, because it really is one of the more unusual objects in the solar system. It orbits Mars at an altitude of only about 6,000 kilometers, closer than any other known moon orbits its parent planet. For comparison, our moon sits at an average of around 384,000 kilometers from Earth. Phobos is practically on top of Mars. It completes one full orbit in just 7 hours and 39 minutes, which is faster than Mars itself rotates. Stand on the Martian surface and you'd watch Phobos rise in the west and set in the east, crossing the sky twice a day. That tight orbit has consequences. Tidal forces from Mars are gradually pulling Phobos inward, by about 1.8 centimeters per year. Within 30 to 50 million years, it'll either collide with Mars or be torn apart, leaving a ring of debris around the planet. Mars is slowly destroying its own moon. On geological timescales, that's soon. Phobos is also covered in a striking system of parallel grooves, long, shallow channels running across much of its surface. The leading explanation is that these are stress fractures. The tidal pull from Mars is literally stretching the moon, and the surface is cracking in response. If that's correct, Phobos may already be weakening from the inside. Some researchers think the interior is largely rubble, held together loosely rather than solid rock, which would make it even more vulnerable to disruption. Then there's Stickney Crater, about 9 kilometers wide, nearly half the diameter of the moon itself. Whatever struck Phobos to create it almost shattered the thing entirely. The impact may also have caused or extended the groove system, though that detail is still being worked out. Deimos is quieter, orbiting much farther out at around 23,000 kilometers. Its orbit is actually slowly expanding. It's drifting away. Smoother than Phobos, craters more softened, generally the less dramatic of the two. Scientifically, though, the origin question applies just as much. So what does any of this mean in the broader context of Mars science? If the giant impact hypothesis turns out to be correct, it means Mars experienced a major collision in its early history, one with significant consequences for how it evolved geologically and thermally. That feeds directly into questions about when Mars had liquid water on its surface, and for how long. The moon origin question and the Mars habitability question aren't separate threads. Phobos has also attracted serious attention as a staging post for human exploration. Because it orbits so close to Mars, and because its gravity is extraordinarily weak, less than 1,000th of Earth's, meaning you'd weigh essentially nothing there, it could serve as a base for remotely operating surface robots before committing to the far more demanding challenge of landing on Mars itself. A Phobos first human mission strategy has been discussed seriously at NASA and elsewhere. There's another angle worth mentioning. Mars ejects material from its surface during large impacts, and some of that debris could have settled on Phobos over billions of years. If that's the case, a sample from Phobos might actually contain a record of Martian geological history, potentially more accessible than drilling into the Martian surface directly. It's one of the reasons the MMX sample return is considered so valuable even beyond the origin question. These moons aren't just an afterthought, they're a compressed record of events that shaped the inner solar system, sitting a few thousand kilometers above a planet we're working to understand in increasing detail. We still don't know where Phobos and Deimos came from, whether they're the remnants of a primordial collision, captured wanderers from the asteroid belt, or something that formed quietly in an early Martian disk. But within this decade, if MMX returns its sample successfully, we'll likely have the answer. That's a genuinely important moment. A century and a half after Hall found these moons almost by accident, we're finally going to touch one. Next time, we bring everything together. The missions that have defined what we know about Mars, the questions that remain open, and where the science goes from here. The episode that ties the whole series together. If you've followed along this far, subscribing would genuinely help. It keeps the channel going, and you won't miss the final episode. The full Mars playlist is in the description, all 6 episodes in order, if you want to watch them back to back. That is part 6 of Mars. In part 7, we explore the next key question. Subscribe so you do not miss it.